So we're going to do a few things today. I have the sense that last time we really went a long way in terms of defining the equations, figuring out what are the quantities that we're interested in, and how they are related. But we need to do some practice problem. We need to do some practical understanding of what's going on, because without practice, we really do not learn enough. So what we're going to do today is we're going to solve a couple of problems. And in order to set a good path for how to solve problems in axial loading, I'm going to remind you what we said at the end of last segment. And that was, how do you go from the loading all the way to the displacement and stresses inside the bar, the elongation, and so on? What is a good path to follow? And what I want you to understand is that this path that we follow now, I'm setting up the problem assuming that somebody comes to me and he tells me I have this bar and there is this loading on the bar. There is some distributed loading, Fx of x. There may be also some concentrated forces, so I may have distributed loading on the bar. Remember, Fx of x is in Newton per meters. And I may have concentrated forces, so the concentrated forces, this will be in newtons. And they also tell me everything. They tell me the geometry of the bar. So for instance, the section here can go to from a big section to a small section. It may also be that the bar is composite. So it may be that inside the bar, for instance, there is a core of a different material inside it. So say that this one here, this bar here is made of maybe one material inside with a certain material modulus and another material outside with a different modulus. So typically in a forward problem, you have your structure. You know what geometry it has. You know what material is made of. You know what cross-section length, and you know the loading. And then you want to figure out what are the stresses inside the structure? What is the elongation? What are the displacements? Okay, so that's like the forward path. Sometimes they may give you things backward. So for instance, in the third problem of your homework, you have a problem in which I give you the destination. I tell you how much the bar elongates. And I tell you there is only one force at the end, and I want you to find the stress inside, which really means at some point you need to figure out what the force is. So sometimes in some of these problems, I may tell you things that look backward, but it's a good idea normally to go forward. You always do your work symbolically. So at the end, when you find your symbolic expression, you invert it to find what you need. So let's go for this forward path. So the first path that the first thing that you want to do in your path, unless the loading is really simple, like there is only one force at the end, so that there's not much to plot. But in general, if you have a more complicated loading condition, it's a good idea to plot your loading. So remember that you're in an axial problem, so the only axis that you have is x. And the only thing you look for the forces is, are they along x, in the x direction, or against x? So you plot them as a function of x. So for instance, here, I would give you a function of f of x. Say that f of x is pointing that way up to here, and then it reverses and points that way on this last part of the thing. So you just go down on your plot, and whatever function I give you, you plot it out. Say that this one is something that looks like that. And you plot it like this. You see this part here goes up because f of x is positive. So you plot it positive. And in this part here of the graph, my f of x will go down because, see, f of x goes negative this way. So it will be negative. Pretty straightforward, right? I'm plotting the x component of the distributed loading. OK? What do you do with these concentrated loads? Well, these concentrated loads, if you have taken your, I think, 1803, the math course that tells you about discontinuities and delta function and step function, this concentrated load in terms of a distribution, they are like a Dirac function. And the way that I want you to plot them is, if they are positive, they go up, just put a big arrow up, double arrow up. with the magnitude. So this is FC going up. Okay, up because it's in the plus x direction. I have an FD here. It goes against x, so you can put a big step here, FD, going down. So this would be like a Dirac function of magnitude FD. But don't worry about it. If you're not done this part in math yet, you don't really need it. But this one kind of gives you a schematic of what the bar feels in the x direction. Concentrated force going up, concentrated force going down, and whatever distributed loading you have. Okay? All right, so you're off to the races. So the next thing that you want to do is you want to obtain your axial n of x, my axial force internal resultant. Yes, thank you.
Can you draw your reaction function like that too, or no?
Well, see, what I'm putting here is the loading. If I were to isolate the bar here, right, I would also have the reaction there. So if I want to also plot plot the bar isolated from the supports, here I would have to put here RXA. Okay? I can do that if you like. It's in the x direction, it would go up. If you plot it this way, what that means is that you expect this plot for everything to work out to go eventually to 0 here. But essentially here is the reaction force at the support. Normally I don't plot it in these problems because I'm really focusing on what the loading is. RXA is an unknown, I do not know yet. But if you want to plot it in, that's the way it would go. It's a concentrated loading positive in x. That's a good question, yes?
How do you know that it's like the...
Oh, I would give you something like, f of x equals sine of x or something like that. That's more like a cosine. But I would give you the function. So for this problem, the description that I'm doing now is for a problem in which I come to you and I tell you what is fx of x. I tell you what is the distributed load shape. Maybe it's ax, maybe it's ax squared, maybe it's 3 minus 2ax squared. You know what I mean? But it's a function. Whatever I give you, plot it out. Okay? Anything else? We're good. Okay. So the next thing you obtain n of x. So how do we obtain n of x? We did this last time, but essentially what you do to obtain n of x, you need to cut your structures at different positions in the bar and obtain it by imposing equilibrium. You do the free body diagram and you impose equilibrium. So for something like this, it would be pretty involved, right? So because the loading is complex. But essentially, to obtain n of x, the step for that is cut at x, generic x along the bar, and then you do the free body diagram. Then you obtain then you impose the sum of the forces in the x direction is equal to 0. And out of this thing, you get n of x. So in this sum of the forces x, what goes in here? N of x can come in here. The concentrated forces will come in here. And this can be plus or minus depending on which way you cut, which part of the bar you take. So we do more examples, but now I'm just going like big picture kind of thing, okay? And then, of course, if you have the distributed load fx of x, you're going to integrate this as well. And all this stuff, the axial loading, the forces and everything, goes in your sum of x is 0. The unknown is n of x, so out of that you get n of x, okay? So that's your next step. So for something like this, my n of x is going to look like that. So I'm going to draw it and then tell you what tricks I'm using to draw it without even doing that thing. So this is going to go like that. Then it's going to go like this. I'm going to come down with this line here. It's going to do like this. This is going to be flat. It's going to come up a bit. And it's going to do, oh, there is a concentrated load here. Forgot that. So what is this concentrated load? I also draw a line right here. It's going to go down a little bit like that. Then here it's going to continue, go flat here, come up here, and go like that. So this is my n of x as a function of x. So the way I would normally obtain this function is by doing all that job. And You saw I didn't do all that work there to do this. I kind of say, it's going to do this, it's going to do that. The way that I do this is you can use the fact that the dn dx is equal to minus fx of x. So we derived this one last time. And you can use this one to check if you did the right job here, but also to kind of get a sense of what the diagram should look like. So how does that work? The way I think of it, I do a trick. So the trick that I do is this one. I imagine that I am looking at this diagram of the loads. And I imagine that I'm here at the end of the bar, and I walk against the x direction. The reason I walk against the x direction is because of this minus sign here. You see that? So I walk like that along the bar, and I look at the way that this diagram points. This diagram tells me the way from my n of x. All right? This diagram tells me here I have a concentrated load up. This tells me when you get here, take a step up. The step up, the magnitude of this step is Fc. Then I have these distributed loads. The distributed load gives me the slope of n of x, right? Because see, that's the slope. So this tells me there is a slope down, and it's more or less constant here, you see? So I slope down, more or less constant. I get here, there is another concentrated load. This tells me step down. Boom, I step down of a step equal to Fd. Then this tells me keep going down, but a little less steeply. So this is like the slope of the ramp. Slope kind of constant here, then the slope decreases, see? Decreases, and here the slope is 0. So I go flat. This tells me start going up now. Start going up. First you go up slowly, and then you go up, more or less at a constant rate. So I go up slowly, and then when I hit what is constant, it's going to go more or less flat like that. You see? I'm just using what the derivative meaning is to kind of get a sense of what my diagram looks like. And of course, because this one are delta Dirac function, the corresponding as you go up would be a step function, right? So I do not know if this helps you. It helps me sometimes if I want to do something quick to see if the diagram of n of x makes sense, if I have a concentrated, confusing, force loading. It helps me to get an idea of what the sketch should look like. It's a good idea if you start thinking in these terms, because this way of thinking is going to help you a lot when we do beam bending. Because in beam bending, typically you have on a beam, you may have distributed load, you may have concentrated loads, and we're going to use a similar trick to kind of get a sense of what happens inside the beam. All right? So your safe path is always cut, get your n of x from free body diagram and equilibrium. There is no error there. It's totally fine. Before or after you have done that work, think in these terms here. Walk your beam, walk your bar, and kind of think the way that the forces point to figure out what n of x is going to be like. Do you have questions? We good? Yes.
Is that graph that you drew, is that the negative function? Or
No, this is n of x. I'm plotting.
Since delta n of x is equal to the negative of f of x?
The derivative of this, dn dx, is equal to minus that. See if it works out. Look. The derivative of this is positive, right? So minus the derivative of that is negative, more or less constant. Here, the derivative is 0. Minus 0 still gives me 0. The derivative of this is negative. I take a minus sign, I get positive. Okay, so from here, you go that way. You go that way by doing dn dx. You take a minus sign, and from this graph, you get to that graph. But typically, you go the other way. So you're integrating in a way. Not in a way. You are integrating, because remember that to do sum of the forces x0, you integrate that one. OK? It's just a trick. I mean, it's a trick based on math, but it's a trick. Do you guys have any other questions? We're good? We're good? Okay. All right. So that's the beginning of your solving the problem. So the next thing that you do is you just look at materials and geometry. So if this is your bar, and you have, as I was saying, something inside which is of different properties like that. So maybe this is modulus E1, and maybe the material inside is modulus E2, and then you're going to have, different cross sections for the two material. You use all this information to do part 3, which is obtain EA effective of X. And remember that this is simply, A1, E1 plus A2, E2 plus whatever, if you have more materials. And each of these can be a function of X. This can be A1 of X. This can be A2 of X. And even the moduli can be a function of X. I think I'm going to give you one problem in which we have moduli that are a function of X. But essentially, given the geometry and given the material properties, you can obtain what are remember what this is called? The effective section stiffness. This tells you how stiff the section is. Something is very stiff if it has a high modulus, a high Young's modulus, and if it is big. Something stiff takes a lot of load to form, right? So something which has a high modulus is stiff. Something which has a high cross-section is stiff. All this information, the section, geometry, and the material, they get put together into this guy over here. So the next thing you do is you plot your A effective of X. So you plot that. In this case, the plot is going to look like it's going to be high here, and then here is going to be lower. And by the way, a lot of this, is that clear enough, right? This is not much to that. It's very important that you notice that in a lot of these drawings that I do, I kind of go slowly from this cross-section here to this cross-section here. See that? I kind of smooth it out a little bit. All the solutions that we do then, we kind of close our eyes to that, and we just imagine that there is a step change in the areas. The reason that I normally draw it that way is because, well, first of all, what we do, the assumptions that we use, and the main assumption that we use is the next assumption coming up, which is epsilon A of X equal. You remember what this is equal? How do I get the strain? What do I need? I need the two things. I need how much load I have and how stiff the section is, right? So how much strain I get, that is how much deformation I get on each section. I'm going to get a lot of deformation if I have a big load, and less deformation if my section is stiff. So see this ratio here? This gives me EA of X, the strain at section X. So when I use this relationship here, what I am saying is that as I look through my cross-section, everybody, both materials, they move by the same amount. What I'm saying with this relationship here is that my strain, how much each section gets strained at every spot, is the same no matter where I am in that section. They all move the same, okay? So these assumptions are good as long as the bar section changes slowly. Something bad happens in structures. So let me do a little aside, okay? So this is an aside, which is a tiny little guy that looks to you like not very important, but this is so important for engineering design. So, and I'll tell you, like this is like a warning kind of design. So it's not like an aside that doesn't matter. It's an aside that actually matters. Okay? So it's very important when you design things to realize that if you make a structure that has sharp corners, like that, and you load it like that, the depth is in the change of sections. See that? See those sharp changes in sections? At those points, our nice assumption that everybody moves the same, the strain is the same everywhere, that breaks apart. It breaks apart because if you imagine that there is a load that these guys are carrying here, and all of a sudden you only have this amount of load, and then it needs to go back up here, something is got to be happening here. This is like there is stress carrying with line of stress through the bar. And all of a sudden, these lines of stress need to get much tighter. It's like this morning I was coming down 93. There was one car stopped at one side, a total mess, a pile up, right? Because all the cars were going along, and then there is a little tightness there. And that tightness means that all the lines of stress need somehow to get together into this tighter spot. And the mess is right here, where things get tighter. So what happens in this point is what are called stress concentrations. So think how stressed you are in the kind of traffic situation. Very stressed. Stress concentrations. That means your stress goes through the roof. Okay, your stress goes through the roof. And your nice simple assumptions that you have in what we do in 201, you can just toss them out in the garbage because they're not good, okay? You have to be very careful when you design things to avoid sharp corner because sharp corners equal death, okay? Now, because I'm not going to deal with that kind of things in 201, I always imagine that my bar changes smoothly, but I do not want to deal with the mess that happens in a smoothly changing cross-section. When we solve this kind of problems, and I draw EA of x, I kind of draw it as if it has a discontinuity there, okay? I can't help myself, though, to put the corners when I draw stuff, to make it smooth, okay? But when you draw things, remember death, avoid death, okay? Are we good? Can I keep going? All right, so when you do things and you see a cross-section that changes from here to here, normally changes over a certain length, we neglect what happens in there. We neglect that length. We just make it change like that. Okay, so we plot now n of x over the stiffness. This gives me the strain as a function of x. And you see that now the strain, I assume that is the same everywhere in the section. And I plot the strain as a function of x. So my strain as a function of x, if I plot it, is going to look similar to that. So it's going to kind of go up, and then, how does that look like? Go down. So if I have the force here, and I have the force here, it's going to go up, and then go down, and then have the step. And then here it was going to do like that, and go flat. But here, because I have a discontinuity in the cross-section, there is going to be a step, because this denominator changes. And so it's going to be a step, because now the strain, because now the strain is going to be less in this chunk here, because I have the same load, but a higher resistance to deformation. And so my strain diagram is going to look something like that for that example. Okay, so I'm making a very complicated example here. But in general, you're going to have a little simpler loading than that. And your fourth step is obtaining epsilon A of x. And essentially, once you've done that, you're home free. So after you've done that, you can more or less say, OK, I'm just about done. So the step 5 is once you have epsilon A of x, with this one, you can do all kinds of things. So having epsilon A of x really means you're almost home free. So with epsilon A of x, what I can do is I can calculate the normal stress. So remember that the normal stress, that's going to be equal to epsilon A of x times the moduli. If you have different moduli, then the stress is going to be changing depending on where you are. So the strain is the same, but if I plot the stress, say that, in this case here, say that E2 is greater than E1. E2 greater than E1, it means the core of that bar is stiff, and the soft is mushy and soft. Okay? So if that's the case, they both have the same strain. So which one is going to have the higher stress, the core or the sleeve? Who's going to be stressed more? I deform them the same amount. The core is stiffer. The core. So the core, if I plot the stress out, the core is going to have this big sigma n, what was that, 2? Sigma n2 is going to be big, and instead the sigma n1 is going to be small. How do I get it? I get the strain at x and multiply by the respective moduli. Yes? Is this assuming that the core has a bigger E? Yeah, that's it. I mean, it's just an assumption just to get you guys thinking of it. Of course, it may be cases in which the core is softer and the sleeve is stiffer. There may be cases in which they may be layered, Okay? All right, so what other thing I can do with the strain? If I know the strain, what else can I get? Displacement. Excellent work. So here on top of this, I can get ux of x. Ux of x, remember that I simply integrate that. To integrate, you have to have your boundary condition. So you must know ux as some spot. So in this place, where would I know ux in this problem? The wall. Nice and simple. So in that problem, I would have ux at the wall. So if I have a wall, then it's going to be 0 at the wall. Plus, I need to integrate from where I have it, x0, to where I want it, x, the dux dx. And dux dx is epsilon a of x. I put x prime because I'm integrating from x0 to where I want it. So this is x. This x is this x. See? Don't mess up the bounds of integration. Okay? And the last thing that I can do, if I want the whole thing, I can get the whole elongation of the bar. So the whole elongation of the bar is how much each little section strains. So each little section strains by epsilon a of x dx. This is how much each little dx get longer. If I integrate it from the beginning of the bar to the end of the bar, I get the elongation. And because of the definition of ux of x, I can also write this, if I want, as ux of L minus ux as 0. Okay? I can write it like that if I want. That's it. That's all the equations that we need to solve this kind of problems. And this is the forward path. And remember that I may come to you and tell you in a problem, delta is equal to 1 centimeter. The bar is loaded just maybe with a force at the end. Get me everything. You're not tricking me. That's what you have to think. You're not tricking me. I know my way. My way goes forward. Even if you do not know f, write everything in terms of f, right? There's going to be an f in all these equations. F, popping up everywhere. At the end, you're going to have delta equal to some stuff, f. And I already know that delta and f are going to be related linearly because all our relations are linear. Okay, so delta is always going to be related linearly to the force that you apply. And actually, this guy here has to do with the stiffness of the bar. So this one here is 1 over k, 1 over the stiffness of the bar for end loads. So after you did all this stuff, you're going to find delta equal to something f. If I give you delta, you just invert it and you get your force. That doesn't mean that you need to start from this end and walk backward to figure out what the f was. Okay? Go forward like a Swiss train. Do not stop. Okay? We good? All right, so let's do, no questions? All right, so let's do a simple example of a design problem. Okay? All righty. So a design problem is a problem in which you're trying to figure out what the properties of the structure should be to meet your design criterion. Like for instance, I may tell you design a bar so that the elongation is this much. Design a bar so that the elongation is this much is a good design problem. So you would have to figure out maybe the stiffness. I can tell you, figure out the modulus for the bar. Or I can tell you, figure out the cross-section of the bar. So my design criteria can be different depending on what my objectives are.